In this video, we explain one compact expression in solid mechanics. Aij times Bij. Both indices are repeated, so the expression is a double contraction. We will derive it, expand it, calculate it by hand, and connect it to stress power, the Frobenius norm, and the J2 invariant. The expression Aij Bij contains two repeated indices. The index I appears twice, and the index j also appears twice. Under Einstein's summation, every repeated index is summed. So this expression sums over both directions I and j. Now we expand the notation. Since I ranges from 1 to 3, and j also ranges from 1 to 3, there are 9 component products. We multiply corresponding components, and then sum everything. The result has no free index left, so the result is a scalar. Let A and B be these two second-order tensors. The goal is to calculate Aij Bij, which is the same as a double dot B. We do the calculation row by row. In the first row, 1 times 4 plus 2 times 1 plus 3 times 0 gives 6. In the second row, 2 times 1 plus 5 times 2 plus 6 times 7 gives 54. In the third row, 3 times 0 plus 6 times 7 plus 9 times 3 gives 69. Adding the 3 row contributions gives 129. The same operation has several equivalent notations. In indicial form, it is Aij Bij. In tensor notation, it is a double dot B. In matrix notation, it is the trace of a transpose B. When the tensors are symmetric, a transpose equals A, so the expression becomes the trace of AB. Now verify the same number using the trace form. A transpose B has diagonal entries 6, 54, and 69. The trace is the sum of these diagonal terms, again giving 129. In solid mechanics, the most important double contraction is sigma Ij times strain rate Ij. This is the stress power per unit volume. The units are Pascal times inverse second, which is watts per cubic meter. This quantity appears in elasticity, plasticity, viscoelasticity, finite elements, DEM homogenization, and thermodynamics of continua. The safe rule is this: identify the repeated indices, sum over them, and then count the free indices left. For Aijxj, the repeated j pair is contracted, and the free index I remains. Therefore the result is a vector yi. For Aij Bjk, j is contracted and I and k remain. So the result is a second-order tensor. For Aij Bij, both I and j are contracted. No free index remains, and the result is a scalar. For Cij Kl epsilon Kl, k and l are contracted. I and j remain, and the result is sigma Ij, a second-order tensor. There is a strict notation rule. In a single term, an index should appear either once as a free index or exactly twice as a repeated summed index. The expression Aij Bij is valid, but Aii is not valid in standard Einstein notation, because the index I appears 3 times. For the Frobenius norm, first write the tensor or explicitly as a matrix. Then Aij means take every entry of A, square it, and sum all 9 terms for this matrix. The squared Frobenius norm is 205. So the Frobenius norm is the square root of 205, approximately 14.32. The same operation appears directly in the second invariant of deviatoric stress. For this deviatoric stress tensor, the double contraction Sij equals 4,600 megapascal squared. Therefore J2 is 1/2 of that value, which is 2,300 megapascal squared. This quantity is central in von Mises plasticity, critical state soil mechanics, and granular constitutive modeling. The memory map is simple. Aij Bij means sum over both indices. It is a double dot B, and it equals the trace of a transpose B. In mechanics, the same operation gives stress power, tensor norms, and the J2 invariant. Operationally, double contraction means multiply corresponding components and sum all of them.